All right, let's talk quickly about the microservices architecture, because I think this is important and it is a differentiator, and it's something that I think is also interesting. So the system is built with three different microservice families. The first one is called the pitcher family, the second one's called the catcher family, and the third one's called the keeper family. Um, you can have multiple pitchers, multiple catchers, multiple keepers. Each one does its a separate and distinct and different set of functions, but they all work together. So the front end, the pitcher here, seen by green, um, is the gateway. It's what emulates the disks to the applications. So this is the front end of our presentation. It maintains and updates the logical view that the applications can see. It's what presents the volume, if you will, on the network so that it can be mounted and used. There's some data compression that goes on. We turn 4 zeros into 04 so that we don't use up as many bits or bytes to store repetitive numbers, kind of basic compression. In addition to, as I explained to you, the organic deduplication, which is done by the catcher. So this application here, the pitcher application here, also is what does the initial hash. So it looks at the ones and zeros that are coming in, and it creates a name. And we can add different kinds of pitchers here. So today we're operating in block volume. The example I've given is block volume. You could run a file system on top of the blocks today if you wanted to. We can also build pitchers, teach pitchers to understand what objects are, to think about key values, for instance, if that became really popular. Different ways that applications might want to talk to storage can all be adapted by the pitcher without changing the rest of the application. So it's not a monolithic, complicated thing to do. We just write a new pitcher, and multiple pitchers can operate in this environment. The catcher, as I mentioned, is the hardest system. It does most of the work with the metadata. It creates those metadata recipes and maintains them, as I mentioned to you before. It keeps track of the time. So this is where we store time. And it also keeps track of heat as well. So this is where we do our heat mapped and tiering decision making. And then finally, the keeper is the interface to the back end, to the storage media itself, to the physical storage. And it keeps track of what's where, what name is stored with what set of ones and zeros where. So it has no idea who's using that block, by the way, but all it knows is that it's supposed to keep track of a block with a particular name, and it does that. It also manages the non-duplication of the data. So it works with the catcher to ensure that we're not writing the same sets of ones and zeros into more than one block. So those are the three elements, the pitcher, the catcher, and the keeper, that come together. Oh, and I should mention that the keeper, just like the pitcher, can be replicated with and trained to understand different types of storage. So today it understands solid state disk, for instance, in the background. We're training it to deal with objects, blobs, glacier, anything that comes along in terms of new storage medium. We can deal with by creating a new keeper or training the keeper to understand that particular type of media. And then you would have, a keeper for your objects, a keeper for your solid state disks, your object store, a keeper for your glacier type store as well. Okay, so that is a quick overview, taking you down a little bit into the detail of how things work inside of ionir. There's a lot of magic in underlying, of course, how this all does operate, but that gives you a sense of what's going on and how we are kind of bending and twisting the laws of physics to provide for very rapid copy and movement of data from one location to another, regardless of the size, and the ability to go back in time. So ionir, as I mentioned before, is a container native storage platform. It does what container native storage platforms do. It does it exceptionally well. It virtualizes physical storage and it presents services out to the front that can be managed and orchestrated by Kubernetes, so that it allows you to build out your Kubernetes environment at massive scale, with Kubernetes doing most of the work in terms of automation and management. It eliminates much of the storage management tasks associated with, previous traditional kind of storage approaches, standalone storage devices and arrays and that sort of thing. And really gives you, storage as a service as part of your Kubernetes rollout. So hopefully this was helpful. There's more information available on ionir.com, and we have white papers, and we have technical people who would love to get in front of a whiteboard and go into great depth with you on this. If that would be of interest to you, then please get a hold of us, fill out the contact us form on ionir.com, and we'll go from there. Thank you. This has been Kirby Wadsworth, and taking you on a little bit of a technical tour of the Ionir Kubernetes native storage platform.